In this video, we will go over how to do an explicit method to solve a partial differential equation in Python. So let's get started. I'm not going to go over the theory. I'll just show you how to do the implementation in Python. So just to remind you, this is the heat equation, and using finite difference method, you can derive the following explicit equation, which is shown over here. This equation lets you calculate the temperature, for example, in the next time level. Okay, so if you go down to the figure over here, this equation represents the calculation of this green value, green point over here. Okay, this green point is calculated based on weighted sum of the previous value or the previous time value and the adjacent values to the left and to the right. Okay, you can also rewrite this equation in terms of the index. So we will say that for this one, for this particular value, we'll call this ti comma j. I is the position index and j is the time index. So that will be equal to ti minus 1 j minus 1, which is talking about this point here in the previous time and previous position. And the next point is ti comma j minus 1, that's in the previous time and the current position. And ti plus 1 j minus 1, that's going to be this point over here. Okay, so let's see how we can recreate this problem in Python. So first let's import numpy as np, and we also would like to plot this at the end of the day. So import matplotlib.pyplot as plt. Okay, now first we want to create the x vector and the time vector. So let's say x equal to np.a range, and it goes from 0 till 1, the step size of 0.25. Okay, and now just to follow the convention here, the step size in the position is h, and step size in the time is k. Okay, so let's keep the same variables here. So h equal to 0.25 and k is equal to, it's also 0.25 here. So this is going to be my position. So here we'll use h, and for time vector t we'll use np.a range, goes from 0 to 1 and k. Okay, now just let's have a quick look at x if it's giving us the same numbers as here. So you can see it only goes up to 0.75. It ignores the last number that you give. So 1 is kind of ignored. So to fix this, you have to push the last number by the step size. So this is 1 plus h and this is 1 plus k. So now it seems to be working. You can check t as well, and t is also giving you the same value. Seems to be working. Next thing is we need to initialize a T matrix, a matrix T which stores all these numbers in it. Okay, so you can do that first. You have to know the size of, or the length of x, how many points are there in the x vector and how many points are there in the t vector. So we'll call this n equal to length of x and m equal to length of t. Okay, then you can create a t vector, the temperature vector, with these many points. So t is going to be equal to np dot zeros, and then use a tuple with n comma m as the size. Okay, so you'll get a empty vector, like the empty matrix like this, with all zeros. Okay, we now need to fill in the boundary conditions and the initial condition. Okay, so first we need to define the boundary conditions. So boundary condition is the easiest one to define. It's all these points over here and all these points over here. Okay, so the index for x is going to be the first one. So t of index for x is 0, and for all the time points. Okay, so position is 0 and all the time points, so you use the colon. Okay, so this will equal to our boundary condition. Okay, we'll set our boundary conditions here. So boundary conditions equal to, so I'll set this as the left boundary is all 0, so I'll type in 0 here, and the right boundary is all zeros as well, so I'll type in 0 here. So the left wall is going to be boundary conditions 0, and the right wall is the last value in the position. So this is going to be -1 comma all columns equal to boundary conditions of 1. Okay, so in case I would like to change it, I can change the boundary conditions over here. Next is the initial condition. So to define the initial condition, we want all the position, so all positions, but we want the first time. Okay, so this is going to be t of all comma 0. Okay, this is equal to the initial conditions. Now what is the initial condition? Okay, in this particular case, the initial condition is sine of pi x. Okay, so this is going to be equal to np dot sine of np dot pi times x. Okay, and that's pretty much it. So let's see if this worked. So you can see it has plugged in numbers over here, and you can see this is in scientific notation, so it's a bit hard to read. So let's just say t dot round up to 3 decimals. And you can see we kind of get the same numbers over here. So 0, 0.707, 1, 0.7, and 0. So that's 0. Sine of 0.25 pi is pi over 4. That's 0.707. Sine pi over 2 is sine 90. That's 1. So it looks to be correct. Now, one thing you have to note is, since we use the first index, the row is defined as your position, and the columns are defined as your time. Okay, so it will look like a transpose version of the graph shown here. So keep that in mind. Okay, now we have the time vector defined. Now we need to calculate the rest of the points inside it. So we need to do for loop. Okay, so if you look at this problem over here, you can see that we need to calculate this position first, and then go to this position, and then this position. Okay, we don't need to calculate the edges because they're already defined. And then once you calculate all these 3 points, you go back and start with this point here. So there should be an inner loop that loops through the position, and then there should be an outer loop that loops through the time vector. Okay, so we start with the time vector outer loop. So for j is the index for time in range of, and the time is defined by m. So m. Okay, and the inner loop is going to be for I in range, and it's defined by n. Okay, okay, so I and j both go from 0 to 4. Okay, and we don't want that to happen. We only want it to go, for example, x shouldn't be starting from 0. It has to start from index 1, then go to 2, and then 3. Okay, so for the position at least, this has to be starting at 1, and it has to end at 3, so n minus 1. Okay, so we have 1, 2, 3, and 1, 2, 3. So this x part is fine. For the time vector as well, you don't look at time 0 because you know the initial conditions. So you can start at 1, the index 1, and you can go all the way till the end. Okay, so this should be fine. So make sure this one starts at 1 and ends at 4. Okay, so this seems to be working fine. Our loops are set up fine. Now it's just a matter of defining your equation. So this is our equation. Okay, let me copy paste it here. So this is our equation. Then it's just a matter of typing out this equation over here. Okay, so it's going to be t of I comma j equal to lambda. Now lambda is a built-in function, lambda, so it will change color like this. So to avoid this, just call it, I'm going to call it a factor, and I'll set the factor to be equal to, lambda we said is equal to k over h squared, right? It's going to be factor times t of I minus 1 comma j minus 1, and that's pretty much it. And yeah, let's look at the t vector now. Again, it's rounded so that, and here you can see the solution has come out like this. So it has calculated all the points in the middle here. So now we have the solution, and you can try to plot it. Just say plt dot plot the t vector, and you will get a graph like this. And when you see that the graph doesn't make a lot of sense. This is usually because of the choice of your step sizes, h and k. Depending on their ratio, your result will converge to the true solution or it will diverge from the true solution. So this looks like something is wrong, okay? Because the temperature starts, let me add a legend as well. So legend is going to be the time vector. Blue line, orange, green, red. So it's going out of, the temperature seems to be increasing as time goes by, which doesn't make sense. So it's to do with the fact that the h and k are not exactly chosen right. So let me change the choice over here to make it more reasonable. So I'm going to change k to 0.025 and I'll set the time to go to 0 from 0 to 0.1. Okay, this will make the step size in k smaller, which makes the factor also small. Okay, so let's try this one. And here you can see we have a better looking result. Okay, and if you would like to improve the accuracy of this further, you could, for example, change the amount of discretization in the x direction. So that's going to be h. Get a larger value set and your curves will look much cleaner. Okay, you can then set the axes labels. plt.x label is the distance in meters, let's say, and plt.y label is the temperature in degrees C. Okay, and it adds that. Another nice thing you can do is you could, instead of having these random colors, you could specify an exact color that you want. So for that we need to plot each line of each line inside the temperature matrix separately. So instead of plotting like this, you can plot just one column. Okay, one column from the all comma. Okay, so you can plot like one line at a time. Okay, so we're going to use a for loop to go through each line and then plot it separately. So we're going to say for j in range up to m. Okay, we're going to plot this with respect to j, and the x-axis is going to be the x value, so that it doesn't do the number of points here. Okay, it's still giving you the same colors that you had last time. If you would like to change the color, you can set another keyword argument here saying color, and you can give it a matrix of values. So if I say 1 0 0, this is RGB, it's going to all come out in red. But we could have a way in which we could convert the red to blue as it cools down, for example, and you could do something like so there's going to be the red color R, G and B. Okay, so we want, when the graph starts, we want to start with red and then eventually it should go to the blue value. Okay, so we can index these numbers here. Sorry, J is our index. So as the for loop is proceeding, it will change the red values and the blue values. So what we need is we need a red value of np.linspace. Linspace will create a vector for you given a starting point. So you want to start with red as 1 and ending point red should go to 0, and given a size. So our size of the vector is going to be m. We're going to do this m times. Yeah, same thing can be done with blue, np.linspace, and blue you want to start with 0, end up with 1 and then same size, and green will set it to 0. Okay, if you run this code, you can have a nice looking graph that goes from blue when time is 0 all the way to time 0.1. So you can see the system is cooling down as time goes. Now for the legend, you could also format this a bit better. You could, for example, create a list which says t equal to, and then it gives you this time. So you can do this using list comprehension. So create a list for the value inside in t. Okay, what do you want to output? You want to output a string that says t equal to that value. Okay, and this only works if you put an F here so that it formats it properly. And now you have this, and you can also add seconds here. Yeah. Okay. You could also format this degree over here. You can just, instead of saying degree, you can do latex formatting here, slash, so inside dollar signs, dollar degree, and it puts the degree symbol over here. And that's it for this lab. Thank you.